Today I want to discuss my plan to teach the lesson of Newton's third law. While I expect that my student is at medium level, they all have to learn about Newton's second law. They all have to learn about Newton's second law, and also they have all carried out some basic experiments that required in this experiment. And now I move on to the main objectives of my lesson. Through this lesson, I want my students to obtain the knowledge of Newton's third law, which states that for every action there is a reaction which is equal but opposite to it. Okay. Besides, I also want my students to obtain some inquiry skills. The first one, they are able to give an tentative answer to the research question. Second, they are able to manipulate the apparatus when carry out their experiments. And third, they are able to compare the results of their experiments with what they have predicted and then get some conclusion about that. So now I move on to the next part, is the strategy I use for my lesson. Since I want my student to truly involved and truly stimulated to ask questions in my lesson, I would provide them some real examples related to the force and reaction force in order to make them feel energetic and enthusiastic and begin into the lesson. Okay. Now I move on to the important part of my lesson, that is key phases of the inquiry-based learning style. The first phase. In the first phase, I will elicit the problem. After real examples and join in some activities, my student will then state out their question. The main question of this experiment is to investigate the relation between the force and reaction force. The relation, okay. The main question is, what is the relation between force and reaction force? Next is the second phase. In this second phase, they're going to solving the problems with experiments. Initially, I want my students to make some assumption about the relation of force and reaction force, and then I would show them this experiment. I do not expect my students to design this experiment on their own, because even I and my friend have made mistake when we first carried out this experiment, since the hidden principle of this is quite misleading to us. So then I do not expect them to design this experiment, but I demand them to go from their assumption about the relationship to some consequence that could be tested with this experiment. Okay. Well, my student will see that there is no dynamometer for them, so they cannot directly measure the forces between the force and reaction force. But they see that here is the ruler and here is a long bar. So they reckon that they would need to make some consequence that could be tested by measuring the distance. Okay? And here's how they will do it. Since they want two cards to exist for each other, they will make two cards collide with each other. My student will make assumption that F12 is equal to minus F21. And hence F12 will equal to F21 in magnitude. And these two cards will collide and interact in an extremely short amount of time, delta t. During the delta t, this short amount of time, these two cards will move with linear accelerated motion. And if this assumption is correct, then they will apply the Newton's second law, and they found out that A2 will have to be equal to M1A1 during the delta t time. And after delta t, the two objects will diverge, separate, and they move away from each other. However, after delta t, they will move with constant velocities. That is, after delta t, they will move with V1 equal to A1 delta t, and V2 equal to A2 and delta t. My student want to see the relationship between force F12 and F21. However, they cannot directly measure F21 and F12. Then they need to see the relationship between another things, and they see that they could relate the relationship between V1 and V2 to see the relationship between F12 and F21, and they see that there is no time device for them here, so they have to deduce another way, and so they think, and they find out that they could make the two cars stop immediately after the same amount of time and measure the distance they have traveled and find out the relation between F12 and F21. That is, after T0, the two cars will stop immediately and they have traveled S1 equal to V1 T0, S2 equal to V2 T0. And from this, they will deduce that S1 over S2 equal to V1 over V2 to A1 over A2 and equal to M2 over M1. Or I write it shorter, S1 This is the consequence my students will test by using this experiment. And here is the table of Here is the table of data I want them to make, and then they will do the experiment record and write the data in the table. Okay, now I will carry out these experiments. First, I will determine the weight of the mass of two objects. Okay.
There's just 2 minutes left.
Yes, 2 minutes left, I know. It is approximately 360 grams. This one is also 360. Now I will carry out this experiment. First, I will mark the position, initial position of two cards. Sorry. Okay, I take this position, Now I will burn the match. And I see the two cards, final position. The moving here, okay. So Okay, I'm sorry, but after they have collected the data, they would see that the data is approximately close to what they have expected, and they get the conclusion that their assumption is true, is accurate, and F12 is equal to F21 in magnitude. So we move to the conclusion that is, for every action there is a reaction which is equal but in opposite direction. And thank you for listening.
There's a few questions for you. First of all, I want to look into the process, the process, especially the reaction time.
Yeah.
It says dramatically short or enormously short. Because it's short, so we can accept the assumption that the force is unchanged. But actually, how does the force change during the reaction time?
How does the force change?
During the reaction time.
During the reaction time, the force, the force that this object acts on this object is changed because the spring is spread out, and since F is equal to kx, the force will then be smaller with that amount of time, a short amount of time.
So it becomes smaller over time.
Yes.
Although the time is very short.
Yeah.
So we assume that the interaction force between the two cars are unchanged during the interaction time.
Yes, because
and then you can apply the Newton's second law for the deduction.
Yes.
But student can ask, hey, the elastic force change, how can you presume the reaction force between the two cars are unchanged?
Well, let's see, because the time is really short. We could see that when they touch each other, the spring is here, and when they move, the spring is like this. It is really short amount of time, so the change in the force could be, negligible. The change in the amount of force is negligible because the time of interaction is extremely short. You see?
That's one way. That's another way you can say we consider the reaction force between the two cars as average force during the reaction time.
Yeah.
The average force can be calculated by the maximum elastic force.
Yes, and the smallest one. Yeah.
And if you do the mathematical calculation in more detail, you can see, well, we can assume that the average force has equal, as unchanged. And there's another student who has said, hey, the string you use to keep the two cars stopped at the same time and then measure the distance. I think it's a little bit short. I want to use a longer string. Can I do that? There's another student saying, wow, it's not necessary to have the string as long as I want to use a shorter string. How can you react to that two questions?
Well, for the students who want to use a long rod, I remind them that this bar has a friction force, and if he or she used the long string fishing line, perhaps it could not extend to the time and make the two cars stop immediately, because since the road is long, even the friction force stop these two cars, this string has not haven't been extended enough. But our main aim of this experiment is that we use this fishing line to stop these two cars immediately, and we need to use this. However, if we use the long road, use the long fishing line, as I has explained to you, this fishing line will not be extended enough in the time that the two cars have stopped due to the friction force.
No, but it's a little bit contradictory with the assumption that after the collisions, the two cars will travel uniformly.
But
and now you say contradict things.
Okay, I'm sorry. We could consider that they move with constant velocity, but in a small distance only. Because we see that when I push this, there is friction force, so that the car stops. but in a very short amount of time, short, then it could be considered that this car moves with constant velocity.
Okay, so the second sentence seems to be right because it says that to use even a shorter string.
But
How can you react?
I think that a shorter string will be hard to, hard for students to measure the distance. Like, for example, when I first carried out this experiment, I set the string like this, and when we burn the match, then after the cars separate, they go back very strongly like this, and they go back like this. If we use the extremely short fishing line, then the two cars will go out and then go in very fast, and they could not determine, the distance they traveled.
That is just a minor effect of sorcery.
Yes.
So take some time to think, and to say that the shorter string will cause more error in measuring the distance.
Yes.
So think about that, and if you can right now, you can think about that and maybe discuss with me later.
Okay.
Think about how you measure the distance. You have to mark the first initial position of the two cars.
Yes.
Yeah. And then it collides and it moves a little bit. And that distance, it is still in the collision, it's still in the interaction time, reaction time, and we do not take that into account in measuring S1 and S2.
Yes.
Because that is the cars moving uniformly. So because we cannot take it into account, it is kind of error in measurement. But if we measure a longer distance, so that distance is small enough, so we can hit like it, something like that. And also we use a raw ruler which cannot measure a very small distance.
Yes.
So if we measure the long distance, so the error becomes smaller. If we measure the short distance, the error is bigger. Because it's a systematic errors, because the minimum length it can measure is only 1 millimeter.
Yeah.
So if we measure 5 millimeters, that's a big error. But if we measure 20 millimeters or 200 millimeters, it's different. Yeah. So something like that we should keep in mind because our students
will ask about
smarter and smarter, and they can also prepare for that.
Yeah.
But generally speaking, you perform well today. Congratulations.
Thank you.
Next one.